Hi everybody. We're going to talk about boiling points. So you may have seen this in class and you may just want a refresher, but here are some of the groups that we talked about in the organic unit: alkanes, alkenes, alcohols, first degree only, aldehydes, ketones, carboxylic acids, esters, amines, and amides. And I'm just going to go through them and explain why they either have low, middle, or high boiling points. So alkanes and alkenes are both nonpolar molecules, just carbons and hydrogens, quite symmetrical usually. And because they're nonpolar, they only have LD forces. But because the alkenes have less electrons than the alkanes, 2 less hydrogens, they have weaker LD forces. So they generally have a lower boiling point. With the alcohols, we can see there that the alcohol has an OH, so it's polar, and it has hydrogen bonding, so it has a relatively high boiling point. The ether has an oxygen that's actually trapped in the carbon chain, so it does have dipole-dipole, but the oxygen is very difficult to get at. And because it's so difficult to get at, it has a relatively low boiling point compared to the alcohol. The aldehyde and ketone are very similar. The aldehyde has the double bonded oxygen on the end, the ketone has it in the middle. The ketone ends up having a different shape, almost an arrow-shaped molecule when it's in its sort of bent form, and this shape makes it stack a little bit better, so it tends to be able to get a little closer, tends to have a slightly higher boiling point. On the test, I'm not going to ask you to compare these two because you have to use shape and not just intermolecular forces. Both aldehydes and ketones have a double bonded oxygen, which is quite polar. So you see a big jump up in boiling point when you look at aldehydes and ketones versus ethers. That's because the oxygen is now exposed outside of the carbon chain and quite polar. In the carboxylic acid, you've got the OH for hydrogen bonding, but you've also got the really strong dipole-dipole with the double bonded oxygen, which is very polar and actually makes the OH more polar. And you have 2 sites where you can have dipole-dipole or hydrogen bonding, so the boiling point jumps up to 141 here. Esters are very much like ketones, except they have an extra oxygen. The oxygen is locked in the middle. Because it's locked in the middle, it really doesn't increase the boiling point very much because it's very hard to get to that locked in oxygen between the 2 carbons. Now, first degree amine, you would expect to have quite a high boiling point because it has hydrogen bonding, but it turns out that NH is very weak. If there's not any oxygen in the molecule, it has quite weak hydrogen bonding. So it only ends up being around 48 as a boiling point with 3 carbons. But in first degree amide, once I add that double bonded oxygen, now I have a strong dipole-dipole site, very polar with the double bonded oxygen, which also makes the NH sites more polar. And so the double bonded oxygen actually strengthens the hydrogen bonding in the NH sites and creates 3 sites for dipole-dipole and hydrogen bonding. Now, if you look at this, you can clearly see the order, and I suggest that you know this order and be able to explain it, and that will help you with boiling points.